Hi, my name is Sumi Alem, and I'm a fourth-year electrical engineering student at UC Davis, graduating this June. This presentation is for the NSF BE-STARSE Spring 2025 internship. The agenda for today. So I will go over the introduction of what my lab does and the research that they do. I'll go over my initial project, my interim project, the setup for the project, kind of what I did and any troubleshooting I had to do, and what I've learned from this project and my future plans. I have been interning with the Controlled Environment Engineering Research Group, which focuses on sustainable hydroponic farming, specifically developing data acquisition, and control systems for monitoring and optimizing growing conditions in controlled environment agriculture. To define hydroponic farming, it is a method of cultivating plants without soil, using a nutrient-rich water solution instead. The main goal of my internship has been to create a system that can collect real-time data from hydroponic setups, things like pH, electrical conductivity, temperature, dissolved oxygen, and turbidity, using sensors connected to an Arduino and Raspberry Pi. Eventually, all this data will be processed and visualized in LabVIEW for deeper analysis. But due to some early delays, mainly lab clearance and issues with the lighting system, I wasn't able to begin the original data collection right away. While waiting for the lab to be fully operational, I pivoted to an interim project, developing an automated flood and drain system using Arduino. This system controls water flow across 3 grow beds. Each bed goes through a cycle, 10 minutes of flooding, 20 minutes of soaking, and 10 minutes of draining. The cycles are staggered, so while one bed is soaking, the next starts flooding. This scheduling helps avoid overlap and ensures continuous operation without needing extra pumps or plumbing. Here's the wiring diagram I worked with. It shows how I connected the Arduino to the relays that control 6 solenoid valves, 3 flood valves labeled FV1 to FV3, and 3 drain valves labeled DV1 to DV3. Each valve is wired to a corresponding relay on the 8-channel module, labeled K1 through K8. The relays are driven by digital output pins from the Arduino. Red wires carry power, black wires are ground, and the white wires carry the control signals. The relay module receives power from an external AC adapter, and the logic pins connect to Arduino pins, the digital pins 1 through 6. Relays are mounted upside down in the panel, so I had to be careful with orientation and labeling when connecting everything. I used a multimeter frequently to verify the correct voltages were outputted from the Arduino to the relays and that each valve was activating as expected. Here's a picture of the full system hooked up. Here's a diagram that shows more carefully the pin connections, which I had to pay really close attention to when writing code. As you can see on the left, there's these pins that from 0 to 13. So these are the pins, the digital pins on the Arduino. So as we can see on the chart I kind of wrote up, so on the right, we can see that 3 and 4 correspond to valve 1, 5 and 6 correspond to valve 2, 9 and 10 correspond to valve 3. And 11 to 12 are hooked up on the system, and we can see it on this diagram too, but we actually don't use them. I initially had thought there were 4 valves, but we did not end up using those 11 and 12 pins. And then on the right, we can see that the relay pins, so there's 4 relays that are hooked up, but again, ion 7 and ion 8 pins on the relays don't end up getting used. So the same, so ion 1 and ion 2 correspond to valve 1, ion 3 and ion 4 correspond to valve 2, ion 5 and ion 6 correspond to valve 3, and ion 7 and ion 8, although hooked up, don't end up being used. And then of course we have the ground and the VCC connections. So initially, I had a lot of trouble writing this code because we couldn't agree on the system, like the timing of the system. So just going back a little bit, so this code that is kind of a snippet of the code. So this code, which was written on the Arduino IDE, this kind of just declares the pins and it kind of corresponds to the chart that was shown before, where it shows the valves. The 3, 4 corresponds to valve 1, 5 and 6 correspond to valve 2, and 9 and 10 correspond to valve 3 that we're going to control with the 3, 4, 5, 6, and 9, 10 pins on the Arduino. So this is what the Arduino pins are being declared. But I had to rewrite, this code was used and it's correct, but what I had to rewrite because we couldn't agree on the timing was the timing part of the code. And I'd actually written 3 different versions, and I'm going to show you each one and how they're a little bit different from one another. So, and this took me a lot of time to get it right. So the first version of the code that I wrote was actually quite simple. So I had initially thought that, oh, this system, how we're going to control it is that my understanding of the timing was that we're only doing 1 valve at a time. So for example, valve 1, it fills for 10 minutes, it waits for 20 minutes while it soaks, and then it drains for 5 minutes. And then once valve one has done all of his business, valve two starts filling for 10 minutes. Valve two soaks for 20 minutes. Valve two then drains for 5 minutes. Valve two's business on is all done, and then it moves to valve three and etc. So for this version of the code, which is shown right now, it's actually very simple. And I was able to use the keyword delay. And in Arduino, delay, it blocks other code from running, so there's no overlap. So, but the whole point is that you can't do tasks concurrently. And this was fine for this version of the code. But then after speaking with my mentor and then other people who were on this team, it turns out that is wrong. We want to do stuff concurrently. So while one is filling and then it fills, and then while it's soaking, already I want another one to start filling while the other one is still soaking. So in that case, there will be some overlap. So this was what is shown here is a version 2 of the code. And this one, how I explained last time, I was able to use delay, but this one I had to switch to using the keyword, the millis, short for millisecond. So why do you have to use this one instead of delay? Is that millis in Arduino, it allows you to do tasks concurrently. It's for concurrent logic. But this version of the code is also wrong, actually, because one, I had built it for 4 valves, and you can actually see the int I equals 0, I is less than 4. You can see that 4 there. So because I didn't know, as I showed in that wiring diagram, one of the valves, it didn't end up getting used, but I didn't know that at that point. So I'd written it for 4. That's one of the errors in this code. And the second is that the timing is still 10:25. It's 10-minute fill, 20-minute soak, 5-minute drain, which we ended up changing. So for the final version and the final timing, right, this is what we agreed on. So we agreed on filling for 10 minutes, sitting for 10 minutes, and draining for 10 minutes. So I kind of filled out this chart to kind of visualize while I was writing my code. I really needed a way to visualize like, oh, like when one is filling, like what is the other one doing? And so this one kind of maps it out. This chart kind of mapped it out for a full hour, and it really helped me while I was writing the code and just to like be able to write the logic that would correspond to it. So for example, while valve 1 is filling for 0 through 10, and valve 1 is just sitting there. But then after valve 1 stops filling, valve 2 can start filling, and then valve 1 is still like soaking at that point. And then once valve 2 stops filling, valve 3 can stop filling. But at the time that valve 3 is done filling, it's time for valve 1 to start draining. So, and again, it's like this logic that we can already see in this chart. But once I had this written out chart, it was really easy for me to like go back and just just make these additional improvements to the code. So as we can see, like how I showed you that last time, it had I less than 4. Now it's I less than 3 because I fixed the valve problem and there's 3 valves on 4, and then I fixed the timing for once and for good. So this final version uses non-blocking timing statements with millis to cycle through each valve's flood, soak, and drain phases in sequence. And I also included logic to ensure that once all the cycles were complete, the process restarts from the beginning, creating an autonomous repeating schedule. So once this code was all correct, the software part was fine. It was time to start the hardware troubleshooting. So one problem that we had right off the bat was that one of the Raspberry Pis were broken, but I couldn't tell which part was broken because the Raspberry Pi was hooked up to this touch screen display, which is shown here. So I had to take apart the touchscreen display and the Raspberry Pi, and then I wanted to see which one was actually broken. So I hooked up another Raspberry Pi to the same touchscreen, and it worked. So that's how we figured out that that Raspberry Pi, the initial one, was broken, and then this new one was working. And then we also had a problem, once we got that problem fixed out, there was another problem that, oh, this Raspberry Pi, this new one doesn't have the Arduino IDE installed on the Raspberry Pi, so we can run the code. And then that was also a huge learning curve for me because one, I've never used our Raspberry Pi, I've only ever used Arduino. So like just learning about, oh, how Raspberry Pi has its own like internet and like has like these really amazing features that I've never seen that aren't even comparable to an Arduino. It's much more advanced. But then that was a learning curve for me because I had to, again, like learn how to install Arduino IDE, and then the Raspberry Pi runs Linux. So you have to install like the Linux version. So just learning all that was really interesting. But once all that hardware was fixed and it was hooked up and the software was running and the debugging and the timing issues were all corrected, and I was able to test the circuits like with a multimeter, we were able to complete the entire system, and this is what it looks like. So this flood and drain system has some really useful implications beyond just our lab. It shows how we can automate irrigation cycles in a scalable and efficient way using low-cost components like an Arduino. And by staggering the cycles, we reduce overlap and conserve resources like power and water. And it's fully autonomous, which means less manual work, and it creates growing conditions for the plants. This kind of setup can be adapted for larger hydroponic farms or even classroom and research environments to teach embedded systems and sustainable agriculture. I'm really grateful for this opportunity. It's been an incredible experience to apply my EE skills in a field like sustainable agriculture, which we don't usually explore in EE courses at UC Davis. And working on real-world systems like this, combining hardware, coding, and environmental impact, has given me a really new perspective on how engineering can support sustainability and innovation in really unexpected ways. So now that the lighting system in the lab has been permanently fixed, the original sensor-based project will resume on June 16th. This summer, I'll shift back to working with ion selective electrodes and developing a LabVIEW-based DAC system to monitor nutrient levels and other environmental parameters in real time. I'm really excited to continue building on this work over the summer and contribute to making hydroponic farming systems more efficient, sustainable, and scalable. Thanks for watching, and I look forward to sharing more soon.